Namaste and welcome to yet another lecture on linear algebra through geometry. Uh, we are in a very interesting topic that we are covering right now. We were looking at the idea of eigenvalues and eigenvectors. We looked at the algebraic multiplicity, geometric multiplicity and stuff, and then we said that we are going to venture into the what do you call the realms of real symmetric matrices, as they find a wide range of applications. So, in this lecture we are just going to look at what a real symmetric matrix is and what are the properties of a real symmetric matrix. We will again take up some examples and we will basically from the examples we will try to get certain insights, and then we will go for proving some of those ideas. So, let us get on to the domain of real symmetric matrices. Okay. So, first of all, what is a real symmetric matrix? So, how do we define this? So, let us take up the definition first of all. A matrix A n by n with real entries and the property that A transpose is equal to A with the real entries and with the property that A transpose is equal to A is called as a real symmetric matrix. This is called as a real symmetric matrix. And if you remember, when we started looking at the vector spaces, we looked at vector spaces of matrices, and when we took square matrices with real entries, basically real matrix of dimension n by n, we saw that the set of all those real symmetric matrices form a subspace of the vector space of square matrices, real matrices, right. We already saw that, which means suppose if I take a matrix A which is real symmetric and I take another matrix B which is also real symmetric, then remember in that vector space case we wanted to prove that the closure under addition we wanted to prove vector addition. We said that okay, you take any two real symmetric matrices, add them, the result must also be a real symmetric matrix, and we took an example there and we said okay, you take ABC, AB, BC and you take another one which is like D, E, F, two matrices, and then you add, you get A plus D, then you have B plus E, then B plus E, then C plus F. So, you see that the sum is also going to be a real symmetric, but let us prove it formally and then look at certain properties. So, let us look at this. The first one that we are going to look at is this: for symmetric matrices A and B, we have already looked at one example of a symmetric matrix which was the projection matrix. We also looked at identity matrix. All these matrices are basically symmetric matrices, and in fact the first matrix that we started working with, which was 2 1 1 2, that was also a real symmetric matrix if you had paid attention to it. So, let us look at this. For symmetric matrices A and B, let me make it for real symmetric matrices. I am going to just talk about real symmetric matrices. We assume that the values are this, the moment I say symmetric matrix, we will assume that the values are also real. So we look at the real symmetric matrices A and B. We want to look at this A plus B, the whole transpose is equal to A plus B. That means the sum of two real symmetric matrix is also a symmetric matrix, right. If you take two real symmetric matrix, you add them, the sum that you get, which is again a matrix, is yet another symmetric matrix. So how do we prove that? We will just take up a simple proof. So we know that by commutativity of matrix addition, A plus B is B plus A, we already know it. So we know that matrix additions commute. It implies A plus B is equal to B plus A. We also know that by the first few classes of this particular course, we would have studied the matrix operations and stuff. We would have seen that the transpose of the sum is nothing but the sum of transpose of the matrices. So we also know that A plus B, the whole transpose, is equal to A transpose plus B transpose. But we already know A transpose is nothing but A and B transpose is nothing but B by symmetry property of A and B, or we will say A and B symmetric. So what do we get? We get that A plus B, the whole transpose, is equal to A plus B, which means what have we proved? We proved that sum of symmetric matrices is yet another symmetric matrices. Sum of symmetric matrices is another symmetric matrix. Similarly, one can establish that if for a scalar k, the second property given a real symmetric matrix and C any scalar, or let us say and K any real scalar, K A is also symmetric. The third most important property is the following: if A is an invertible real symmetric matrix, A inverse is also real symmetric. If A is an invertible real symmetric matrix, A inverse is also a real symmetric matrix. Now, this we can do a simple proof of this wherever the second property is I have not proved it. So, I would request the viewers to just try out the simple proof. The proof is pretty simple. Please go ahead trying out the proof. Let us look at this the third property, the proof of this. So, let us do this. We know that A inverse A is equal to A inverse is equal to identity matrix, and we know that identity matrix is symmetric, that I transpose is equal to I, right. So, we have A inverse is equal to I is equal to I transpose, which is equal to A inverse the whole transpose. Now, what do we get? This is nothing but A inverse transpose into A transpose. So, if we try to rearrange this, what we get is like A inverse, we get this rearranging we get A inverse A is equal to A inverse the whole transpose into A transpose. Now, what I do is I multiply throughout a post multiply by A inverse. So, what do I get? I get A inverse A into A inverse is equal to A inverse the whole transpose A transpose A inverse, but A transpose is equal to A, which implies A inverse into identity matrix is equal to A inverse the whole transpose into the identity matrix, which implies A inverse is equal to A inverse the whole transpose. That means, the matrix A inverse is also symmetric. So, what we are going to do is we are going to say that if A is an invertible symmetric matrix, A inverse is also symmetric matrix. Now, what is more interesting as far as the what would you call, as far as the real symmetric matrices are concerned, let us look at the eigenvalues of a real symmetric matrix, right. We will take some examples and see what is it that we get, and let us try to prove that, I mean whatever that we see, let us see if that works. Okay, so, what are we going to do? Okay, consider A is equal to 2 1 1 2. This is the matrix that we have been working with for quite some time. So, we have 2 1 1 2, and we know that the eigenvalues for this matrix, we have already done it, let us do it again. So, we have determinant of A minus lambda I is equal to 0, which implies determinant of 2 minus lambda 1 1 2 minus lambda is equal to 0. So, we get lambda square minus 4 lambda plus 3 is equal to 0. So, we get 4 minus 1 plus 3, which is equal to 0. So, we have lambda minus 3 into lambda minus 1 is equal to 0, which implies lambda is equal to 3 and lambda is equal to 1. Note that this matrix A is a symmetric matrix. That is a symmetric matrix, right. Let us take this example. So, what are we going to do? This says that okay, I have something interesting, I found the values of lambda to be 3 and 1, and what does that mean? Lambda is equal to 3 and 1, that means you have real values, right. Okay. So, now what are we going to do? We are going to look at the following. Let us take a simple general matrix. So, consider A is equal to, let us say AB BC, real, and we have already seen that the transpose of this matrix is the matrix itself, therefore, A is symmetric. Note that A is symmetric, real and symmetric, right. Okay. Now, let us try to find out the eigenvalues of this particular matrix A. So, let us find out, the eigenvalues of A. Now, what do we mean by that? We form the characteristic equation and solve for the find out the roots of the characteristic equation. So, we have, which implies A minus lambda I is equal to A minus lambda B C minus lambda. This is what we have. So, and what we have, the characteristic equation is determinant of A minus lambda I is equal to 0, which implies the following, which implies we have A minus lambda into C minus lambda minus B square is equal to 0, which implies we have lambda squared minus lambda times A plus C minus we have minus lambda, and so we have this AC and then we have this minus B square. So, we have minus B square plus AC is equal to 0. So, what are the roots of this equation? So, we know that the roots of this equation is the roots of the above are lambda is equal to, we have this minus b plus or minus root of b square minus 4 ac by 2a. So, we have this minus b is nothing but minus of minus a plus c. So, you have a plus c minus of this a plus c term. So, you have a plus c plus or minus square root of b square, which is nothing but a plus b the whole square, minus 4 ac minus 4 into a is 1 and c is ac minus b squared by 2a. This is what we have. 2a, here a is equal to 1. So, let me make that 2, right. So, we have this. So, let us expand whatever is there in the bracket. So, I am going to have a plus c plus or minus square root of a square plus 2 a c plus c square minus 4 a c plus 4 b square divided by 2, which implies I am going to get lambda is equal to a plus c plus or minus square root of a square minus 2 ac plus c square plus 4 b square divided by 2, which is nothing but again a plus c plus or minus square root of a square minus 2 ac plus c square is nothing but a minus c the whole square plus 4 b square by 2. Now, if you look at the term under the square root, this is basically sum of squares which will either be 0 or positive numbers. That means, the values under the root, I mean the second term, which is basically this guy is going to be whatever is inside, that guy is going to be a positive number or 0. So, let us look at both the cases. So, let us look at this. So, basically a non negative quantity is what we have. So, we know that the value a minus c the whole square plus 4 b square is always greater than or equal to 0. Hence, the square root is always real. The square root of a minus c the whole square plus 4 b square is always real. Right, it is always real. So, that is what we have. So, now what we do is we look at two cases. So, and then we will get back to a concluding statement for that whatever we found out. So, let us take this. So, case 1, case when a minus c the whole square plus 4 b squared is equal to 0. What happens when a minus c the whole square plus 4 b square is 0? Now, this implies sum of two squares is 0, that means individually they must be 0. So, we have a minus c is equal to 0, which implies c is equal to a, and 4 b squared is equal to 0, which implies b is equal to 0. Therefore, our matrix A now, therefore, the matrix A, the matrix A now becomes A is equal to, we had A B, B C, but what does it say? From here we found B is equal to 0, A is equal to B is equal to 0 and C is equal to A. So, we have A is equal to a diagonal matrix. Suppose if A minus C the whole squared plus 4 B square is strictly greater than 0, then we already know the roots. What are the roots? The roots are basically lambda is equal to, we have this A plus C plus or minus square root of A minus C the whole squared plus 4 B squared by 2. So, what is the conclusion that we are going to say? We are going to say that, of course, we will generalize this for any n by n matrix, real symmetric matrix. We will generalize this result at least for 2 dimension, at least for a 2 by 2 matrix, real symmetric matrix. We figured out that the eigenvalues, the eigenvalues of a real symmetric are of a 2 by 2 matrix are real. The eigenvalues are also real values, right. Now, Let us look at one more interesting property of the real symmetric matrices, and then we will try to do a summary of whatever we have done this. Then we will take up a general case, right. Then we will, in the next lecture, what we will do is we will look at the general case, but right now let us do one more property. So, consider the product A transpose A. Now, what is A transpose A? So, where A is again a real symmetric matrix. So, what is the product A transpose A? How is that matrix going to be? So, let us look at A transpose A. So, let B be the matrix which is obtained as the product of this matrix A transpose A. Now, what we want to do is we want to figure out what is B transpose. B transpose is A transpose A the whole transpose, which is nothing but A transpose into A transpose the whole transpose. We know that A transpose the whole transpose is A. So, we have A transpose A, and B transpose is again B itself, right. We see that B transpose is equal to B, which means we are going to say that the matrix A transpose A, the product A transpose A is equal to B is also a real symmetric matrix. Right. And if you look at A transpose A, we can take that to be A transpose is A itself. So, A into A it becomes, so A transpose A is basically our A squared that we get. Similarly, we can also look at the similarly the product A transpose is equal to say some C matrix is also symmetric. Let us prove that. So, C is equal to A transpose, C transpose is A transpose the whole transpose, which is nothing but A transpose the whole transpose into A transpose, which is nothing but A transpose. So, therefore, we have C transpose is equal to A transpose, which is equal to C itself. So, that means this product, the A transpose, the matrix that you get out of the product A transpose is also a symmetric matrix. And what is interesting is we will soon see in singular value decomposition, when we do, we will use this product matrix A transpose A and A transpose. We will look at all this in our singular value decomposition, which we will soon see in the next module. So, what we have done right now is basically we have looked at a couple of we have basically looked at the idea of real symmetric matrices. What a real symmetric matrix means, that means a matrix whose transpose is the matrix itself is what we call, and whose entries are real, we call that as a real symmetric matrix. And we looked at certain properties, and the most important and interesting property that we looked at was the property pertaining to the eigenvalues of a real symmetric matrix. We figured out that at least in the 2 by 2 case, we can prove that the eigenvalues of a real symmetric matrix are real. We also looked at some of these product matrices, namely A transpose A and A transpose. We proved that they are also symmetric. Now, what we will do is, in the next lecture, we will extend this result, whatever about the eigenvalues of real symmetric matrix being real, we will extend it to and see, we will see whether that holds good for any n by n matrix, real symmetric n by n matrix. And then what we will do is we will again go back to 2 by 2 to figure out what happens to the eigenvectors of the real symmetric matrices with distinct eigenvalues. Suppose I have a real symmetric matrix with distinct eigenvalues, what can I say about the eigenvectors of this? This is also something which we did when we did 2 by 2, but then we will generalize that result now and see that, look, oh, there is something interesting that happens. And once we have done that, it becomes easy for us to explain the action of a matrix A on any vector, especially the matrix A being a real symmetric matrix. We will look at all that in the next lecture. Thank you.